Yeah, so I am working with Vikram at IIT Tirupati with Vishal and my collaborators shown here under the SETI Technosignature grant. And Vikram has already given you an idea about what I'm going to talk about. But before moving on, I would like to mention two members, Shambhavi Jaiswal and Ibrahim Matthews, who have contributed a lot to building the machine learning model and coming up with training methodologies. So moving on, this is what I'm going to discuss. I'll just start with brief introduction of exoplanet discoveries and then move on to the work that we have been doing. All right. So yes. So without this question, just like an FRB repeater, I have to keep repeating this question probably until we actually find an answer as yes. So moving on. So what the question from are we alone to seeing how far we have come or how close we are still to finding answer to that question. So the purpose of showing you this slide is to give you an idea of how many exoplanets have been discovered, and there are like close to 6,000 now, and maximum number around like 3/4 of them are coming from transit method studies. And what has emerged is the variety of the population of exoplanets that have come out, with rocky planets and ocean worlds occupying a large fraction of these discoveries. So what makes us hopeful is the existence of these Earth-like planets, which are probably very similar in terms of the nature of their surfaces. So we are very hopeful of finding either a biosignature or technosignature detection in one of these exoplanets. So our hopes are very high, and my belief to the question is that, of course not, and probably many of you will agree with me. So let's just move on to the next slide. Because transit method have contributed to a large fraction of discoveries, I just want to briefly introduce, in case you don't know what transit method is, which is just basically, okay. So as you, any planet that is going around its star, if you keep looking at the star, then you will see as a function of time, the stellar light keeps varying and you will see periodic dips in the stellar light curve. This is what is referred to as light curve. And these periodic dips are the indication of presence of a transiting system. So transit missions like Kepler mission, which has already been completed, that I'm going to talk about more in detail later, and the TESS, which is Transiting Exoplanet Survey Satellite, and the upcoming Plato are going to contribute a lot to the sample of light curves. So the question is, how can we use these light curves for our technosignature search or not? So what we know from these light curves is that the ingress and egress, which means when the planet enters the transit and when it exits the transit, has imprints of the shape of the transiting system. So this is our aim, that we want to image the shadow or the 2D projected image of the transiting system from its light curve. So yes, so moving on, I'll just mention quickly the Kepler mission, which has been the NASA's planet hunter, and it has looked around 150,000 stars in our Milky Way galaxy. And what it did is to look at a very fixed patch of sky continuously for 4 years. And to give you a perspective of what it did, such deep observations, I'll just show you a cartoon picture. It's not as nice as other animations that you may have seen, but it'll give you an idea that if you take if this is sun, then there is a planet Jupiter sitting at the center, which is 10% the size of the sun, and you may be able to see, I'm not sure, a tiny dot at the center, which is like Earth, which is even smaller, which is only 1% of the size of the sun. So the question is, if we try to, so if we try to I just try to zoom in to show you, to be able to see these tiny planets there, then you will see that the Jupiter, if Jupiter is orbiting the star, you will see only 1% change in the light curve or the depth of the star. Whereas if you look at Earth-like planet, it will be even smaller, like much smaller to detect by any ground-based telescopes. So what Kepler has achieved is this unprecedented depth, close to 20 parts per million, which is in principle able to detect even planets half the size of Earth. So that is in some sense, the revolution of the Kepler, and it has so far contributed to close to 3,000 exoplanet discoveries alone using this method, and there are like 1,000 to 2,000 still waiting to be confirmed. So we want to use this large amount of transit light curves to do our study. All right. So yes, this is the aim. We want to find anomalous transiting shapes. So what does it mean? So I'll just give you quickly the idea. Let's say for the timing, we know what are the shapes of the transiting systems, and we also can find what is the corresponding light curve that one observes from these stars. So then what we want to do is to take this as a labeled input data set, so shapes and the corresponding light curves, and we want to build a machine learning model to be able to, which is here, to be able to tell us what the shapes of these transiting systems are, and later quantify them as whether they are part of normal planets, which will give us roughly the circular shape, or whether they are something different from planets or some weird shape. So this is the idea. This is the whole picture of what we are trying to do. And how this will contribute to technosignature is what Vikram has already mentioned, that the Dyson disks are something that one can look for, the weird shapes that we will look for, which will be the best candidates for technosignature searches. Okay, and given the large amount of data, a machine learning approach is going to be best suited to do this kind of study. Okay, so the step one is to get these variety of shapes to be able to train or to be able to give it to the model, machine learning model. So what we have done is to generate all kinds of shapes, from circles, ellipses, symmetric shapes to weird shapes, and this forms the sample of the shapes. So now we have also rotated the shapes to increase the number of samples. And the next step is to actually find the corresponding light curve. So to do that, what we have used for the time being is the 8-bit transit package. What it does is, if you have a grid, which is basically an opacity map with the values between 0 and 1, and you just make it pass across your star, it calculates how much of light you will receive from this star, given that these black pixels would be blocking some of the light while transiting the star. So this is, we are using this, and you can find this paper link here. So just to mention that we are not using the UT code that Vikram mentioned earlier, because it is computationally very expensive. So for the timing, this is what we are using to generate the light curves for given shapes. Okay, so yes, this is our training model. It's a simple convolutional neural network, which is not very deep, and the input is the light curve. So we have standardized all the light curves to be between 0 and 1, so depth is 1, and also the transit is such that it is always at the center of our input light curve with 120 points in total. All right, so I'll just explain what under what assumptions we are generating the light curves. So we have assumed that the impact parameter is 0, which means the planet always transits mid-plane with respect to the star and with respect to the observer, and the transiting body does not rotate about its own axis. And there is only single structure at a time that we are trying to model. And we have also included the limb darkening model for the star. Okay, so the very first results that we want to show is the predictions on the test data. So on top of that, on top of the light curve, we have also added Gaussian noise after scaling. And we want to then just give these test light curves to the machine learning model and see what it predicts, what shape it gives us compared to the ground truth. So you can see in this figure, the ground truth is shown in the rightmost column, and the predicted shapes are shown in the corresponding row, with the ratio of planet to star decreasing as we go along this direction. So what it means, we have also encountered for the size, the differences in the sizes of planets and star. If you want to know the details, I can explain later. But given the different sizes of planets and the SNR that we have introduced, for a high SNR light curves, we are able to predict shape to quite good accuracy, I would say. And another thing that we do is to check what happens if we increase the noise in the light curves. So with the increased noise, we can see that the predictions become less accurate for almost all radius ratios. And this is the limitation for the time being, that for a good SNR light curves, we are predicting very good predictions for the shapes. Okay, so two conclusions is, as we decrease the radius ratio of planet to star, the predictions deviate to some extent from the truth value, and prediction map also degrades with decreasing SNR, which is expected. Okay, so another result is just testing it, how the model performs on Kepler light curves. So here I have shown 6 best SNR light curves from the Kepler data, and the prediction maps are shown here. So you can see that most of them are looking very circular, and there's only one that is not that much circular. The question is, if we are able to predict a circular shape for the Kepler light curves for the confirmed planets, then we can say that our model is performing well. On top of this, another very interesting result that I want to show is the prediction map on the exocomet light curve. So what we did is to take the exocomet light curve, which is a fit to the real light curve from Ziba et al., and we have given this light curve simply to this model to see what it predicts. And what you can see is the shape prediction kind of matches with our expectation of what a comet looks like. So this is very fascinating as well as encouraging, and I'll explain why. So another thing, one of the criteria that we have to do is to identify how do we say whether the prediction maps are circle or not. So to do that, we come up with a very simple approach where we take the prediction map, we find out where is the boundary of this emission in some sense, and then just fit a circle to it and find out how much flux is out of this circle versus how much is inside. So for the timing, the criteria that we are using to decide whether something is circle or not is given by this. So for a threshold of 0.95 and a distance deviation of 10%, we are going to call that as a circle. So what do we see, what do we do next is for this particular shape, it's obvious that it is not a circle, and we are getting, this condition is working well to predict that this shape is not a circle. So we take all the Kepler light curves which are above 700, which are in number in 700 with SNR more than 50, and we just see how many of them are predicted as circles or not. So with the condition that we mentioned earlier, around 46% of the Kepler light curves are predicted as circles. And in case we relax this threshold a little, we are getting 78% circles. So what the point of showing this is that even though the Kepler, we have not optimized the model and the training as required by the Kepler data, we are still able to predict with at least half the fraction of planets at circle. So there is a high, of course we need to improve the model and the parameters according to the data, and especially take care of the noise. But this gives us a hope that this model is, even though it's simplistic, it's going to work as we are expecting it to. So this is my summary slide to say that even with our simplistic convolutional neural network, we are getting very encouraging predictions of the light curves. And even though we have not accounted for the Kepler noise exactly, there are also, you may have thought of the degeneracies which are coming due to various factors, that if you have a shape which is just vertically flipped, will give you the same light curve as the shape which is not flipped. So these are the areas where we have to improve, specifically related to the real data. And the current model is predicting good, giving us good results. So it's very hopeful and encouraging. And we are planning to improve this. We are planning to improve the model as well as by incorporating the Kepler noise itself to see how we can make the predictions better. Along with this, I just want to mention that we also have recently a new postdoc has joined us recently, Isabel, who is also going to continue this work on the test data. So we hope to get interesting predictions and results very soon. So thank you.
Thank you, Gitika. Any questions?
So I have one question regarding the assumption that you take that like along the mid axis, but in the real scenarios, wouldn't be there like many exoplanets which will be transiting away from the let's say the mid axis?
Yeah, there would be, but the thing is that you will not observe them using transit methods. For transits, you need to mostly or most of them will be edge on. Otherwise, you will not see the dip significantly. So that is the reason that we assume the impact parameter to be close to zero. Also with Kepler data, also the impact parameters are not really that high. They are close to zero. So that is why the assumption, I think, is still valid even for real scenarios.
Thank you.
Thanks, Gitika, for that approach for this problem. I'm just curious, is there some specific reason why you are still testing on Kepler data and not test data, which I think is focusing more on the brighter sources? So it would be more convenient, I guess.
No, Kepler is focusing on the fainter.
Yeah, that's what I'm saying. So maybe testing on tests would be more convenient.
Yeah, we are planning to do that. I mentioned that our newly joined member Isabel is going to work on that. I have not. That is the next step. So we have just tested it on Kepler data. We are going to test it on test data and improve the models accordingly to the requirements of individual data sets.
Also, does the noise change between different missions? So like, will you have to work from scratch for different data sets?
Yes, when it comes to noise, yes, we have to understand the noise really well to be really be confident about what we are getting. So, and every mission has its own characteristic noise properties. So we have to account for that in each mission. For the time being, maybe we'll come up with something where noise may be accounted for in some general way, but for the time being, no.
Okay, thanks. That works. Thank you.
Yeah, there's one question here.
Yeah, so other than Dyson disks, what are other anomalies what that might reflect, the shape variations or something like that in light curves?
Anything which is not circle would reflect in the prediction maps. So one such example that I gave is an exocomet, which is obviously, you can see that even in the light curve, it's a very weird thing. So those weird objects plus even the tiny deviations from a planets are a good, we can't say what they are, but we have to look for at least the anomalous things. Then we can maybe follow up and see what we can do with that.
Yeah, there's one question. It's Neil.
Thank you for the nice talk. Did you try with your simulations of how much higher the SNR needs to be to get a good percentage for the prediction of a circular shape?
Yes. So for SNR up to 500, we are getting up to 200, we are getting good predictions, and the fractions roughly remain the same, little bit here and there. But as we reduce the SNR to below 200, like 100 or even 50, then the predictions are not that well. So there we have to improve now.
Thank you.
Thank you, and let's thank Gitika once again. And
Yeah, everyone.